Okay, you probably have things popping up now saying that we're going to do that. So thanks to the speakers for letting us record the meeting. So just the usual one slide of introduction. So welcome back to the Compute Accelerator Forum in 2022, everyone. We are in the process of planning the meeting series for this year. So if there's anything that you would like to present, or if you think there's a topic which is interesting and we should cover it in the Compute Accelerator Forum, then please get in touch with the organizers and we'll hopefully be able to fit that in. Just to remind people that we, just to keep things easy in the calendar, we have the scheduled slot of the second Wednesday of every month at 16:30 CERN time. I'm very happy that today we're going to kick off with two talks from our colleagues in the HEP-CCE project covering I/O and portable parallelization. Just as a further reminder, if you want to make sure that you get the meeting announcements, sign up to that mailing list at CERN. And let me just give you a heads up that for our next meeting, we will have on the 9th of March, a joint meeting between the Compute Accelerator Forum and the HSF Software Triggers and Reconstruction Group. So we look forward to seeing everyone in a month. But I think that's all that I had by way of introduction. So I will stop sharing. And then, oh, just to note, by the way, Indico is broken. So you won't be able to see the slides just yet until we fix it, but the speakers have their copies, so they'll be able to go ahead. And also to remind people that there are live notes available. So if you would prefer to ask a question in the live notes or just make some interesting comment or observation, then just go to the link that's there in Indigo. Hopefully that will work. Yeah, I think Ben has posted it in the chat, and we'll be able to take your question from there. I think with that, I can first of all pass over to Charles, who I think is going to give us a few words of introduction about the overall project, and then we move on to the specific slides. So take it away, Charles.
Great, thank you, Graham. Right, well, and since there are no slides to download, you guys are all going to have to pay attention while I talk for once. All right, I'm going to talk about the High Energy Physics Center for Computational Excellence today. And we're going to start with me giving a little bit of an introduction, then we're going to hand over to Peter and Saba to talk about some of the iOS implications, and then we'll return to me to talk more about parallelization strategies. So why do we have this Center for Computational Excellence? And everyone knows the issues that we're facing. We've all seen these very depressing slides. Our resource challenges are enormous. Run 4, Run 5, HLHC, and beyond. We're needing huge amounts of both compute and disk, much more than we think that we can budget for right now. And one of the places that we might be able to find all of these resources is in the world of the HPC. And HPC has been heavily used by high energy physics for quite a while, but maybe not quite across the board. It's really been a platform of choice for like the cosmic frontier, and we've certainly been seen used it for certain types of simulations and event generators, but it's not necessarily used for all of reconstruction. And the challenges that we're really facing with HPCs is they are evolving in a direction that we are not particularly comfortable with right now. In the next decade or so, we're going to see way more compute power available on HPCs than we can actually use. Several orders of magnitude more will be available than what our projected resources are, but they're going to be in a way that we are not able to use particularly well. And that really means GPUs and other types of compute accelerators. For the past long time, our computing universe has really looked like this. When's the last time any of us used something other than an Intel? When was the last time we used a VAX or an Apollo or an SGI or something like that? It's been, what, 30 years maybe? And AMD has also made inroads, but AMD, really the slide should be x86 inside as opposed to just Intel inside. The architecture has really stayed the same for a very long time, and we've become very, very good at using it. Our compute stack has become very optimized for x86 architecture. But HPCs now and coming are really starting to look like this. They've got a tiny little bit of Intel inside or x86, and all the rest of the compute power is coming from accelerators. And it's not just one type of accelerator. It's not just an NVIDIA GPU. We also see Intel GPUs and AMD GPUs, and we start seeing some other weird architectures like Fugaku, which has very, very wide registers. They're kind of GPU-like, and we're also seeing FPGAs starting to come into the mix. So who knows what it's really going to look like in the next 10 years. But what we do know is that it's probably not going to be just CPUs. So we are faced with some really major challenges to use these kind of environments. We've got lots of different computational sites, institutional and grid clusters, the clouds, HPCs. We have many hundreds of C++ kernels, which translate into millions and millions of lines of code. We have lots of different types of data objects, which tend to be dynamic and polymorphic, which makes writing them out very challenging. And we have a lot of non-professional developers, domain experts, what we call, physicists. These people are not really incredibly expert in writing good C++ software. On the other hand, we have a lot of opportunities because we have very large experiments and a very broad community. So if we try, we can actually bring a lot of R&D firepower to the game. So where we actually see inroads starting to be made in using GPUs is right now on things like the online system. If you look at experiments like the LHCb and ELISE, we see them making heavy use of GPUs for their DAQ. We also start seeing use of GPUs in offline pattern recognition, meaning tracking and things like that, and also in detector simulation. So this is where CCE comes in. It is a 3-year pilot project, which is intended to develop practical solutions on how to port all of these different kernels to this diverse range of hardware architectures, and to collaborate with the HPCs and networking communities on very intensive data use cases. It's split up into 4 parts. The first is the portable parallelization strategies, which is trying to find ways to use the massive concurrency that we see on HPCs and to do it in a way that can actually be done portably. So we only need to write the code once as opposed to having to rewrite it for every single different architecture. The second one is our IO issue, or our IO group, which is looking at storage issues like new data models and fine-grained IO and how to do event batching. We also have a group which is looking at optimizing event generators, where there's a little bit of overlap between that and the PPS, and I'll spend a little bit of time talking about that as well. And finally, we have a group which is looking at complex workflows, because our workflows are very different from the traditional ones that we see on HPCs, which tend to be very homogeneous and very, very linear. And our workflows, especially in like the cosmic frontier, are very, very different, and they do not map well onto HPCs. So without further ado, I'm going to hand this off to Peter and Saba to tell you about the iOS parts.
Yeah, thank you, Charles. Maybe we switch over and Saba can share the screen, and then I will introduce the second project, or the second part of the project you mentioned, the iOS project. Thank you, Saba. I can see your slides. We can go to the next one. So the main or the overriding goal of the HEP-CCE iOS project is to make event processing on an HPC possible. And for that, we have a few goals which we are working on, which I listed here. So the parallelization, the parallel serialization and deserialization of our data models is a very important ingredient to be able to capture wider concurrency. Our data model representation need to be tuned and optimized for these high-performance computing systems. And we need to be able to access partial sub-event data blocks, the fine-grained reading and writing will be part of our goals to investigate. And then lastly, but not least, so runtime memory data mapping to take into account offloading to these accelerators Charles mentioned is an important goal for us. Next slide, please. To work towards these goals, we have a few main activities where we do development and research on. And they're all guided by the underlying principle of achieving efficient high-performance I/O on an HPC. Our first activity, which Saba will go into detail, is doing I/O profiling using an HPC tool called Darshan, where we have the developer, the main developer is part of our HEP-CCE iOS group, and we are using that tool to do studies and adjust that goal and adjust that tool to fit our HEP use cases. We are doing root serialization and scaling studies because root serialization, given the complex data model which we have to persistify, root serialization is a very important tool, and we want to tune it and optimize it for those use cases. Then we are investigating alternate I/O formats that may be better suitable for an HPC. In particular, HDF5 is something which the HPC experts are very familiar with, and we are investigating that for use in HEP data. Lastly, again, we are looking at, and we are really just starting out to look at memory-friendly data. We do that in collaboration with the PPS groups to make data more offloadable to a GPU or accelerator. So those are our main activities. Saba really will go into detail on this. Let me give you, thank you. Let me give you just a snapshot on who is involved in these activities. Now, this is just a random snapshot of one of those meetings. But as you can see, it's rather a diverse crowd of characters from many of the DOE labs in the US, and from both sides, HEP experts and HPC experts from the computing sides, and from several experiments, Atlas, CMS, Dune are represented here. Okay, with that, I give it over to Saba, and Saba will walk us through the details.
Okay, hello everyone. Thank you, Peter, for the introductory slides. And before I start, I just want to say that the material and work for iOS is contributed by many of our colleagues, and I will acknowledge as I go through these slides, and I will try my best to convey the material and answer any questions that you may have, but I may need refer to the team members. I already see some of their have connected. And with that, I will start with the first topic. That is on IO profiling studies with Darshan, and I have listed the material was provided for this talk by these people. Okay, so some of these bullet points are taken directly from Darshan's website, and the key points are that Darshan is a scalable HPC IO characterization tool that is able to capture an accurate picture of applications IO behavior. It can be used to investigate and tune the IO behavior of complex HPC applications. So it can identify IO bottlenecks in multiple processes on multiple nodes writing to a shared files. It records all the POSIX and stdio for each process and store in a Darshan file. And there are tools available to generate PDF files and with the detailed info that can be analyzed manually, and we can deduce what is performing good or not. So next slide. Since I mentioned that this is an HPC tool, so for non-MPI HEP applications, we have successfully used Darshan We have used it for CMS, Dune, and Atlas's frameworks, and it was built as a dynamic library, for example, for CMS, and that's how Patrick has done some of these studies. And I believe some similar was done for Atlas and Dune as well. So the initial work was to integrate Darshan into our workflows, and we were successfully able to generate logs for example workflows from each of the 3 participating experiments in here. And the analysis of these workflows showed already that, we see a lot of small access patterns, and this is a known thing to be not very friendly for the parallel file systems on HPCs. And this work also resulted in enhancements to the tool itself. For example, the library was made fork safe to support Atlas use case. There were features like runtime configuration to control memory usage, and then to figure out what files to instrument and what to ignore. So those kind of features were added to Darshan as an outcome of this project. Although we have logs from all 3 experiments, and we have these detailed reports on all different phases, I just picked one, and this is just one step from CMS's workflow, so just the reconstruction step. The point to show this overloaded report here is to give you an idea that what kind of information we can get with Darshan, and then we can actually go back and see how we can improve the situation, whether it has to come through the workflows or whether it has come through the tool or the IO system that we are currently using, such as root. And it can also tell us that, maybe we want to use different block sizes, or what would be the best strategy to move forward. There is, so one thing I wanted to just point out here is that you can see the small access here, and you can see the count that, most of the accesses we have were reported to be very small. So this is just a glimpse of the data, the detailed data that we have and we will have for the more realistic workflows. And with that, I will go to the next slide. So what is next is that we really need to now expand on this work to look into characterization and tuning of the workloads for HEP use cases, so that we can see how we can use that on HPC storage. So as Peter mentioned, that we have the right experts. We have the experts from the Darshan side. We have experts from root. We have experts from the experiment side. So we have the right combination, so we can go ahead and do look into realistic production level configurations. And the goal would be to identify bottlenecks that are worth investigating. And then we need to implement changes to workflows and or root as needed. Then in terms of reporting, how we can enhance those things. So there are a couple of items here as well, that we need to have workflow aware reports using a set of Darshan logs, which we already have. So having DAGs of workflow phases and what files were accessed, and then also file and file system access patterns of different workflow phases. And then the last would be to have more trace-based visualization, so that we can have read and write access patterns for files produced and consumed by different workflow phases. So with that, I will move to the next topic. So this is another main area that we have been working on. But this material and mostly work is done and provided by Chris. And we are looking, so this is gonna cover the test framework for data formats comparison and root serialization scaling studies. So we need to test different storage formats for use on HPC, and we need to be able to compare read and write performance scaling with the number of available cores. And also we need to study, the memory usage scaling and the file size comparison. And lastly, the large scale usage impact on HPC sites. And in order to do all that, we developed, we developed a simplified HEP multi-threaded framework. So the work is based on, or the core concepts are based on CMS's framework. High levels of concurrency are supported, and events can be read, processed, and written concurrently, and data products and events can be written and read concurrently as well. So the serial processes are scheduled by framework, and they never block a thread. So for example, if there are multiple events that want to write to the file system, so their requests are queued and only one happens at a time, while the other threads, they can be used to do other work. So the framework, I think the most useful feature is that it can support any number of storage formats. So that actually serves the purpose that we really need it for. So all we have, if you want to bring in a new storage format, so all you have to do is implement the necessary base class interfaces, and then you will be able to read from any supported format and write to any supported format. So we can read Atlas, CMS, and Dune experiment root files, and we can just use real data for testing as well. And so there is nothing in the code that is like very much tied to the experiment itself. But when we run things, then we have to do experiment specific setups, because we are using the input root files, and we have to set up and make sure that proper dictionaries and everything is available. So the next couple of slides will discuss testing performance of writes. So it will just cover that what was done. We used CMS as a smallest data format, and the time spent in reading was minimized. So basically, read just first 100 events and then cache them to memory. Okay, can I just finish first? Okay, so read first 100 events and then cache them to memory, and then replay them, the cache events over and over. And then the number of threads was kept equal to the number of concurrent events. And intra-event concurrency helps whenever we have serialization happening. All the cores of machine were kept busy. That is, we ran just as many jobs that will keep all the cores busy. The number of jobs is basically whatever number of cores were available on the machine divided by number of threads for that particular job. And the formats that were tested, so 3 formats were considered in this performance testing. So the first one is a standard HEP root format. Events are stored as an element in a T tree, and each event data product in it has its own T branch of the T tree. Then there is a simple per event storage format that was designed to support concurrency. And then the last one is root with 1 blob per event. So, the way it's done is so explicitly do object serialization, and that is done concurrently, and then store all the data products for an event into 1 blob. Then for compression, there are 2 options. Either we can do concurrently, and we can just do it externally. And the other option is to do something with root, and but then that compression is done serially. Okay, Next slide. So here are the results. With this setup, the first reading, when I looked at this, and I was like, so the simple concurrent is performing very well. And I checked with Chris, and Chris, the way Chris describes it is that, you know, we see the 10% difference, and with that, the simple format is better. But we need to also consider the flexibility of the concurrent compressed root blob method. So that brings more flexibility to the mix. And so maybe, you know, that may be an okay or a better trade-off to call that one a better approach. So this is like one of the many, I would say, a lot of studies that were done, but this is the most recent ones. And probably we can have like a whole big talk on the topic. With that, I will move to the next topic, where now we will bring HDF5 into this mix of data formats. And our goal is to evaluate that if using parallel file formats such as HDF5 could be beneficial for storing the intermediate data coming from HEP workflows. So this work is the first attempt to write this kind of data to HDF. Okay. So just a very brief introduction, like I did for Darshan. If you already not know, I will just quickly go through this. So hierarchical data format. So the interest is that it is widely available and optimized on HPC centers. And so that's and it supports parallel IO using MPI, and then it has everything tuned for parallel file systems. The few key abstractions in this hierarchy are groups and data sets and attributes, and it allows efficient columnar access for the required data products. So the design assumptions that is coming from the test framework. So now we have established that we have this test framework, and we can it is very straightforward to add new data formats to the framework. So that's the step we are at, and now we are trying to add HDF5 to the mix. So the input data is already serialized with root. And so we understand that there are complex objects, but what is presented to HDF5 is just a byte stream. Also we are not working with the analysis ready data either. That is like the n-tuple data, which is more, I would say, a direct mapping if we have to look at to the HDF5. So we are interested in designing an experiment independent approach. So again, there is not going to be any experiment specific assumptions in the implementation. But I think I have said it before too, that we will need experiment specific setup to just be able to run it when we are running with root, to make sure all the dictionaries are available. So here are some details of about Hdf Outputter. So what we are doing is that we are organizing data similar to what we have in the standard root format. So each data product gets to be stored in a different data set in an HDF5 file. And then we need a corresponding way to make sure that we remember what are the event boundaries for each data product. So we basically do 2 data sets per data product. So we accumulate or aggregate writes before we events before we write to the file. So then the rest of the things are a little bit more details that I can maybe a little bit skip over, and then I can just raise the immediate issue that comes up with this kind of format is that, you know, we were generating a lot of metadata, and we were generating thousands of data products, basically the data sets, because if you have thousands of data products in your data set, so that is equally translating into the data sets. So with that, we looked into some improvements and alternate layouts. So both of these are work in progress because we still have to evaluate. But the idea is to reduce the number of IO calls on metadata related data sets. So we basically collect metadata for all data sets for each event and then save them once. And then the other approach is to implement another Hdf outputter. And it is similar to what was done for root, the blob, the event blob based format. So we are doing exactly the same layout in HDF5 as well. So now the number of data sets is reduced to 3 as compared to thousands. And again, work in progress, and we are hoping to just bring that into the test framework in a form ready to be compared with other options. But both of these HDF5 implementations are general and straightforward to adopt for incorporating parallel design. So far we have just covered HDF serial design. So the data we have written, we are able to read that data. Currently, only the data product based is complete, but I think the good feature is that we are able to read events randomly, since we can index it to the data set as needed. So if that is like a primary use case, so then this looks this may be like a good way to think about organizing things. So for us, the next steps are to do the reading performance evaluations and then write HDF source for reading the event block format, because that's not been done. Okay, with that, I will just talk a little bit about running tests on HPC. So just it's non-trivial to set up and be able to run with any experiment data and code on the HPC machines. We haven't tried running anything with Atlas or Dune data files on Cori at this point, but we have locally done with all three. But we also know that Atlas is using this kind of HDF5 design and strategy with their framework, but not in production, but it is, they are working with it. We can run the test framework with CMS reconstruction files and some, I think, AOD files as well on Cori. And we are evaluating performance and going back and forth with our collaborators at Berkeley to see that, in addition on an HPC node, how we will see things. With that, so just touching a little bit on adding the parallelism, like the multiprocessing support to the mix now. So we have a multi-threaded framework. So now we have also created an MPI-based version of this application. And our goal is to evaluate multi-node performance as well, right? And and make sure that we are all set to do parallel IO using HDF5. So there are 3 supported modes. So in each case, you will have n MPI ranks. So either you are reading n input files and then you just produce that many output files. It's a trivial case. Then in the other thing, you can read just one input file and then everybody writes the part of file that they worked on. I don't know how realistic that case is, but that can be done too. And then the last one and the most important one is ability to write to one shared output file. And this is the mode that we are working on. It is not completed yet. And in the next slide, I will touch on it as well. So we do have an independent prototype of parallel HDF5 writing capability, and we are working to incorporate that into the test framework so that it can be uniformly studied along with the other options. So the idea is to, and MPI ranks, they participate in the reading of file and then write to a single file collectively. And then with writing a file collectively, the benefit is that the final file will not need merging. right? Or if you have final couple of files, so then again, the merge cost may be, you may have to use less resources. But I think the key concept here is that since multiple ranks are writing to the same output file, we need to figure out how to assign the position of the data within a data set, and how to index events properly so the events, so the ranks are coordinated properly to make sure that they are not stepping over, no data is missed, and they write the whole event worth data on their allocated assigned index and not exceed the size. So use of MPI functionalities to communicate with various, so in order to implement that, we have to use MPI functionalities to communicate with various processes so that the relevant information for collective IO can be exchanged. And so use of parallel HDF5 API to do the reading and writing by various MPI nodes collectively. So we are doing this already, but there were, since this was based on the serial design, and now serial design is also being improved, so we are trying to converge to come up with a system that can be testable. So this is again a little bit more detail, a very colorful diagram where I just wanted to depict the idea of that, how this process looks like to when you write to single file by multiple ranks, and at one time, one data product, you can write that in parallel, and then once that is done, then you go to the next data product and next data product. And so all the data set writing is within data set is parallel, but across data sets is not. And just to add last point here, that with the event blob approach, so this design is going to become much simpler because now we have very few data sets to work with. Okay, with that, I'll come to the last topic, which is about GPU-friendly data model. So the work is just begun on this, and right now a very rough draft. And I'm just realizing that I did not put the people in here. So Amit and Lisa and Kyle are, and I will update the slides. But this work is just starting. We need so what we are looking is to have like a serializer tool for persisting the complex C++ objects, which may not be possible in the GPUs. And so we are looking for data, data structures that will not need secondary tools to do persistence. So like I said, very initial phases, and hopefully in the coming meetings, there will be more to talk about. With that, I'll just summarize about all the main areas of work. So Darshan has been a very useful tool to guide us about HEP workflows, their IO patterns and usage on HPC. And this work has already resulted, in some suggestions, and also resulted in enhancements to the tool as well. Root serialization scaling studies, a whole lot was not covered in here, but with close collaboration, like with working with Philippe and the team, so there were many opportunities that were uncovered to improve, and so all the frameworks that are using root, so those things are kind of eventually be getting there. The test framework, it provides us a very, I would say, a valuable tool that can be used to do performance comparison among different IO strategies and formats in an experiment independent code. And then the last is that, we are working with HDF5 with parallel IO support, and we are evaluating it against other IO formats. So we'll see how things go. And so I see a raised hand. I have just 1 or 2 slides, and then I'll take the question, if that's okay. So for HDF, so there are a couple of things that HDF5 experts in the team are suggesting, like the event aggregation and HDF grouping. And then HDF has also some work done in multi-threaded areas too, but we aren't using it, so exploring that might be good. And then they also have done work to direct access with the GPUs, so that might be worth exploring. And then the overall, like, for the test framework, so we do need to do read performance tests. We do need to do a lot of these testings on HPC nodes. And we have to test the HDF5's ability to, write the multiple, from multiple processes. Scaling on HPC is critical. Multi-node testing is critical. And so in short, we need to compare and evaluate, different formats and perform any optimizations that are needed and conclude that, which one is a viable choice. And, and the important thing to keep in mind is that what is the realistic usage pattern? We are dumping this data to HDF5 or to the sequential, to root or to a simple formats and all that. But what is the intended use afterwards? And that can also help us guide to do these things better. And I think with that, this is my last slide, and I'm happy to take any questions. Okay.
Thank you, Saba. That was really interesting. And thanks to Charles and Peter for their introductions as well. So yes, indeed, we have a couple of hands up already, and Attila was first, so fire away.
Yeah, thanks a lot for your presentation. Let's say I have two questions. First, since you talked so much about reading experiment-specific data, what do you mean exactly when you say that, for instance, you are able to read Atlas root files? Did you build the necessary code, the necessary dictionaries for reading it, or what does
yes
it?
Yes, right. So I think I will have Peter talk specifically about things with Atlas, but I can tell you that, for example, to run anything with CMS root files or the CMS data or even the Dune data, so there were like different setups that were being done. So we were making sure that all the dictionaries are present and all the necessary steps were done so that we can read those data. So that's what I mean, that, for different experiments, you will need to do that.
Yeah.
Sorry,
so you need to, for the Atlas case, you would need to do the A setup. You would need to be able to link against the dictionaries, but there is no code dependency within our mimicking framework to either of the experiments. So you can either use it with Atlas data if you're in the Atlas environment, or with CMS.
Okay, but sure. Then I understand. You just picked up the pre-built dictionaries and everything. Fine. The other one is, I was a little bit unsure about, you just very quickly mentioned GPUs here at the very end. So is the idea here to investigate serialization and deserialization happening in GPU code? Or what is it exactly that you're trying to do with data structures and GPUs?
So maybe I take it, this question. So this is a program that really has just started, and it's not yet clear. I don't think we are envisioning serialization and deserialization happening on the GPU. I think we are more looking at whether we can find a data model that is simple enough so that it doesn't need CPU-based deserialization to be amendable to a GPU. But it's really just starting out as a
because
project.
I guess you guys know that many people are trying to crack that nut, including NVIDIA together with the Arrow developers. So there is interest in that, but it's not a simple problem to solve.
Yes, so it's a hard nut to crack, and there is existing effort, and really what we have is just the seed of an effort going there.
Okay.
Thanks, Attila, and for the answers. And Javier, you're next, so go ahead.
Yeah. Hello. Well, first of all, thanks for the nice presentation. I have, say, 3 simple questions. First one is that you said that you are using HDF5 to store objects as a byte stream, so the serialized representation of an object. So how does that play with? Are you using? So I guess if you are doing that, then the representation on disk is not columnar anymore, right?
Right. So so the idea here is if you so the last point that I said was at the end of the talk that we need to understand how we want to use this data, right? But the way it is stored, the serialized data, it is columnar in the sense that you can access a single data product easily, and you can index through it easily with this pattern, if that is your use case.
Okay, so it's not fully columnar as in a data member per column or something like that, but like sub objects per can be accessed at that granularity, right? Mm-hmm. Okay, so yeah, I'm asking this because I, together with Jakob, were working the last months of 2021 on a comparison about Aaron tuple T3 HDF5.
I think we talked, right, at some point.
Say again.
I'm
Sorry?
saying that I think we talked at some point with Jacob.
Yeah, we did. Okay. We did in the past. Yeah.
Okay.
Yeah. And yeah, my second question is, well, the slides were not numbered, so I cannot tell you to go back to a specific slide, okay. But it was that slide that was showing how the mapping was done with MPI and how the output results, this one.
Okay.
So this, the question was about the results at the output. So these colorful rectangles, represents data sets, or is it a distinct output file, or?
So these are data sets. So this whole colorful block is one HDF5 file. And then each colored band is one data set. And then within that band, so there are, like, you can see 4 partitions. So those just show that the data product, different sizes, just to represent that was written by each rank.
Okay, thanks. Thanks for the clarification. Yeah, much clearer now. Okay. And yeah, my last question is because well, I will start first with the question. Are you using HDF5 compression, like the set-leave integrated compression?
No, I have not used any HDF5 compression so far. We were just hoping to have like an optimal design in terms of layout, and then we can look into the different compression options. So we are not there yet. Yeah.
Okay, great. Because in our comparison that we did in November last year for ACAT, it turns out that the main bottleneck that we detected in HDF5, both in the row-wise and column-wise representation that we were doing, it's basically that the compression happens only on a single thread, and that's for multi-core machines is obviously a bottleneck. And yeah, that was the rationale of the question.
Okay.
Yeah, that was all. Thanks a lot for the talk. Very nice talk.
Thanks, Javier.
So any other questions? I don't see anything in the live notes. Just raise your hand if you have something. Meanwhile, let me pop in, and I was just wondering, you're obviously very conscious of the fact that it's important to examine the right use cases for these kind of studies. And I was wondering if you had, for instance, like concentrated on analysis jobs, because clearly when you look at with a broad brush at the kind of workloads which we run in high energy physics, analysis jobs are the most IO demanding of all of our jobs.
Not in this project, but in different contexts, yes.
So let me add a sentence here. So a job being IO intense is not the only indication to use a different format. It's also functionality. And I think HDF5 gives us this collective IO, which might be even useful for jobs that are not that IO intense. If you have several different nodes writing very little, that's not an IO intense job, but you may want that very little to be collected into a single file, right? And then there HDF5 may help. So we are looking at HDF5 more as a general extension of our toolkit beyond root. Not that there's anything wrong with root, but it would be nice to extend that.
Yeah, thanks, Peter.
Also,
I think that's a valid point there. Yeah, Chris.
There's one other point about that, which is that production jobs in CMS are limited by their output, not by disk speed, but by compression and everything else, and it doesn't scale. So highly scalable, thread scalable output is necessary to make use of many core machines.
Thanks, Peter. Chris. So last call, any other questions people would like to raise? Okay, I don't see any. So I think with that, thank you again to Saba and Peter. And let's go back to Charles and hear about the portable parallelization strategies in HEP-CCE. So take it away, Charles.
Great, thanks. All right, so picking up with what we call PPS for short, for portable parallelization strategies. What we have wanted to do is basically look at a bunch of different portable APIs or portability solutions. These are things like Cocos, Raja, Alpaca, the whole SYCL ecosystem like SYCL, DPC++, HIP-CCC, OpenMP and OpenACC, and a recent addition has also been the STD parallel execution extension that was introduced in C++17, and now we're actually starting to see compilers that will allow offloading that to GPUs. And what we have done with these different APIs is we have taken a number of different, somewhat representative HEP test beds, which are standalone, and tried to port them to each of these, or actually we're in the process of porting them to each of these different portability solutions. We have PataTrack from CMS, which does pixel tracking. There is P2R also from CMS, which does the propagate to R step, another a little further out tracking. There's the Wirecell Toolkit from Dune, which is doing liquid argon TPC simulation and reconstruction. There's fast Gallow Sim from Atlas, which does a parametrized simulation of the Atlas liquid argon calorimeter. And also another recent addition is ACTS, which is a common tracking framework. And what we have done is we have tried to define a set of metrics really to try to evaluate how good or how appropriate each of these individual APIs are to the different test beds. And I'll spend a little bit of time in the next slide talking about that. And then in the end, what we're going to do is circle around and take everything that we've learned from this project and then make recommendations back to the experiments. And what's really important is that we don't expect to have a one-size-fits-all solution. Different experiments are going to have different requirements and different styles of workflow. And they could very well mean that the recommendations for the best portability solution will be different. So this is kind of where the ecosystem is right now with the different types of portability solutions on the different hardware backends. CUDA is the bog standard really for running on GPUs these days, but unfortunately it is the least well supported. It only runs on NVIDIA GPUs, which is why we're doing all of this work. Cocos is a really up and coming in that we are seeing very rapid development on new platforms such as the AMD GPUs and the Intel GPUs. A couple of years ago, those blocks would have been red and they're not supported. But right now we have, the AMD version, the AMD backend of Cocos is feature complete, even though it's still marked as experimental. And there are several different prototypes for the Intel GPU. One is a direct implementation in Cocos, and the other one uses the OpenMP target offload. DPC++ is also expanding rapidly. We now have solutions for NVIDIA GPUs from 2 different providers. There's both CodePlay and the Intel LLVM branch. the AMD can be targeted by HEP-CCE and also the Intel LLVM branch. For HIP, we also see some very, very early developments using the HIP-LZ backend to run on Intel GPUs. Alpaca has some development now for Intel GPUs, and the AMD GPU backend is under development. And the OpenMP offload, I think, is the one which is really best supported across the board. There's a row there for Fortran. We don't tend to use Fortran very much anymore, thank God. But it's very prevalent in the HPC community still, so that's why it's included here. And I think now it's really time to start adding Python to this mix, because now we're starting to see backends for different things like Numba, for instance. Numba can not just run on CUDA, NVIDIA with CUDA backends, but now we're seeing products that will enable it to run on AMD backends. But as I said, this chart is really changing pretty rapidly, and every few months the shades of green and red and orange start changing. So let me spend a slide talking about metrics. So basically, how do we evaluate how good each of these different?
Just before you move on, Charles, Andrea put his hand up. Andrea, do you want to wait, ask the question now, or wait until the end?
I'm writing comments in the live notes, so you can go ahead with the talk.
Okay, that's great. Thanks. Sorry for the interruption, Charles.
Oh, no worries. So we have developed a bunch of both objective and subjective metrics to try to evaluate these different portability solutions. Things like how easy is it to learn, how much code do you have to modify, how hard is it to modify, from just CPU code to one of these portability layers, or from an existing CUDA solution to a portability layer, or from one portability layer to another. What impact does it have on things like your EDM? Does it take over your main? Does it play nicely with the threading backends like TBB, which are currently heavily used in a lot of different HEP software? What impact does it have on your build infrastructure? Does it play nice with CMake? Do you have to recompile your entire software stack? Then there's things like hardware mapping. Is the product rapidly undergoing development? Do we see when new hardware features are available, are they quickly supported in these software backends? How well are new architectures supported? Do they have the full feature availability? Things like reductions and kernel chaining and callbacks. Does it support concurrent kernel execution, which I think will be very important for us coming on? Is it easy to debug? NVIDIA has a very nice software suite of debugging tools. That can't really be said for some of the other platforms. And when you throw things like another API layer into it, it becomes considerably more challenging. We also need to look at the ability to target different types of workflows. What happens when you have a lot of different kernels? What happens when you have only just a few number of developers? Is there a good support stack for these different solutions? And then do they work better when you have a compute-bound task versus a memory-bound task? Then we also have to look at long-term sustainability. Are these products going to be around for a long time? CUDA is going to be around for a long time, but is Cocos or Raja or Alpaca? I think some of them, yes, because they're used by a lot of different experiments right now, and some of them, it's much more questionable. Finally, you have to look at things like compile time. Does it really impact how long it takes to build? You know, for Atlas, we take a very long time to build our entire software stack. If suddenly it went from taking a few hours to taking a few days, that becomes really problematic. And then you'd think that how fast does it run on the GPU would be right up there with number one, but frankly, I don't think it's the most important factor. If you can't use any of the GPU, then you have zero, your speed is zero. So even if you're running at 50% capacity on the GPU as opposed to 100% if you use CUDA, that's still a huge win over being able to not run at all. And finally, you have to look at things like validation. How closely or how hard is it to reproduce your original either CUDA code or CPU code? And then what does it look like? In the end, how challenging is it to read code? Because when you do software reviews, aesthetics, I think, is very important. And how does it work into the whole status of compatibility with emerging C++ standards? All right, so now on to the different test beds. Let me start off with PataTrack. So PataTrack is a standalone version of the CMS's heterogeneous pixel tracker and vertex reconstruction. What it does is it copies the raw data to the GPU. It performs a bunch of kernels there where it does things like decode the pixel raw data, clusters the pixel hits, forms doublets, and then forms quadruplets. So basically it's doing seed finding. And it tries to keep as much of this on the GPU as possible, because you really don't want to mix things back and forth between the CPU and the GPU, because that'll kill you in the end. And we have a number of different solutions for it right now, portability layers. Right, we've been focusing on Cocos for the start, and so we have the original CPU version with a CUDA port and then also a HIP port, and then the Cocos port has been able to execute on the NVIDIA GPUs, AMD GPUs, and also on multi-threaded and multi-core systems using the OpenMP and POSIX backend. We also have an Alpaca version, which has just started to be under development, and there's some of the results which are shown in this ACAT poster that I've linked. Let me just, though, talk about the Cocos performance. It's somewhat hard to compare because Cocos doesn't really support everything that has bing done in PataTrack in terms of multi-processing and multi-threading, and things like doing having multiple concurrent CUDA streams, or doing memory caching on CUDA. So in some ways, it looks like it performs relatively well. For instance, if you look at the direct CPU versus the Cocos with a serial backend, you're looking at 25 events per second versus 24 events per second. That looks pretty good. But when you start increasing the number of processes, the ratio changes substantially. We're looking at almost 50% reduction in performance when you have when you load up a node on Cori, for example, or I guess with 40 processes. Yeah, this is on Cori or on Perlmutter. When we look at the Cocos backend, or the CUDA backend of Cocos versus the original CUDA backend, we see less good performance. With just one concurrent event, we're looking about 900 events per second versus 600. And as we increase the number of concurrent events, that changes dramatically as well. We're looking at 2,200 versus less than 1,000. So we definitely see a significant performance degradation when we increase the number of concurrent events, either on the CPU or on the GPU. And there are a lot of different reasons for getting into this, and I don't really have time to go into this, and maybe one of these days we'll have a whole talk just devoted to this, because I think it's actually worth going into. But if we look at this Chet paper, we've talked about it in a little bit more detail. So let me go on to Wirecell, so June is, and a lot of it, other liquid argon TPC software is based on a product called Larsoft, and it's single-threaded and has a really high memory consumption. The Wirecell Toolkit is a new standalone package which is made explicitly for liquid argon TPC simulation, signal processing, reconstruction, visualization, and it's written in modern C++ that follows data flow programming paradigms. It supports multi-threaded execution as well as single-threaded, and can handle multiple events in flight. The Wirecell Toolkit that we have been looking at includes central elements of the June analysis, such as signal noise simulation, noise filtering, and signal processing. And we've had a CUDA port of the signal processing and simulation modules that show some really promising speed up. We have focused mostly on COCOS at this point. We have basically taken the CUDA port and converted it, and we have really 3 steps of this. There's a rasterization step, which takes the deposits, where you have about 100,000 or several 100,000 deposits for a single cosmic ray event, and it turns them into these little patches, which are a small 20 by 22D arrays. Then there's a scatter add step that takes these patches and turns them into a big grid of about 10K by 10K. And finally, we have a fast Fourier transform that does a convolution step with a detector response. And we have seen some good speed ups when using GPUs, and reasonable performance when using the COCOS backend when we compare to CUDA. We have looked at the CUDA backend of COCOS, and we see about 33 time speed improvement over the original CPU. We've also exercised it on the AMD GPUs, where the performance is considerably worse. It's only about 10 times faster than the CPU, and also the OpenMP backend. And the OpenMP backend really performs, not much better, maybe a factor of 3 times better than the original CPU. And that really has a lot to do with how the FFT step is able to use the OpenMP. And there's some threading issues and multiprocessing issues which are going on there, which really slow things down. When we increase the number of concurrent processes on a GPU, and especially when we're using multiple GPUs on a system like a Cori or a Perlmutter, we can actually see some pretty good scaling, up to about 4 processes. After that, though, we don't really see, or 4 processes per GPU. After that, though, the performance tends to drop off. That's because we're really filling up the GPU at that point. And we can't get, even with MPS, we were saturating the GPU, so throwing in more processes doesn't really help, and in fact tends to hinder things. Next on the docket is the P2R, or Propagate to Radial, which is a mini app that's extracted from CMS's MKFit. And what it does is it has a bunch of kernels for track propagation and the Kalman update step in the radial direction. And it's pretty small and lightweight, and it was really intended to explore these types of portable parallelization strategies and the new technologies. We have versions for TBB, CUDA, COCOS, OpenACC, STD-PAR, HIP, and Alpaca. And right now we've been focusing on measuring the performance of the CUDA with the COCOS backends, and well, actually all the backends for COCOS. And also we've just started looking at STD-PAR. And if we compare the performance of these to the CUDA backend, we see reasonable performance for things that target NVIDIA platforms. The CUDA backend for COCOS and for OpenACC are at about 80% of the full CUDA speed. STD-PAR is maybe about half the speed. And we're just started looking into that right now to figure out exactly what's going on. The AMD GPU definitely doesn't work nearly as well as the NVIDIA one, and the COCOS implementation which targets the HIP backend also performs not nearly as well. It's looking at maybe 60% versus 80% that we saw with the CUDA backend. Fast Gallow Sim is a product from Atlas, and what it does is it does a parametrized simulation of the liquid argon calorimeter in Atlas. The liquid argon simulation in Atlas, the original one was written in Géant 4, and because of the complex geometry of the liquid argon as accordion calorimeter, it's very slow. So in order to really speed up the process, where we're using a really significant number of our total compute budget was spent doing the simulation for the liquid argon calorimeter, we developed this parametrized simulation, which is somewhat less accurate, but enormously faster than the Géant 4 simulation. And so the fast Gallow Sim is a code base that we extracted from Atlas as a standalone version that basically reproduces what is done in the original code, and was originally ported to GPUs using CUDA, which is a relatively small kernel of maybe 4 kernels, one which does a memory initialization, another which does the actual simulation, then there's a stream compaction step, and then everything is copied back to the CPU. We have taken the CUDA port and we've ported it then to a number of different APIs after that. It is very small, and it definitely tends not to exercise the GPU very well, especially when we look at just single events and single electrons. And in fact, we can run about 60 concurrent processes on a machine like Cori without really saturating the GPU. If you want to get better performance, we really have to look at higher energy events or starting to mix multiple events in a single event, or maybe gang events. When we look at the actual performances of the various backends, we see some pretty interesting things. The CUDA backend performs about 5 times faster than the original CPU version. And the Cocos with CUDA backend performs roughly par with the original CUDA. We've also ported it to HIP or used the exercise, rather, I should say we've exercised the HIP and the p-thread and the OpenMP backends of Cocos, and we've definitely seen different levels of performance there. For instance, using the OpenMP backend, we only see about 2.5 times performance with 12 threads compared to the original CPU. So that's definitely not really good bang for your buck. The HIP backends show some significant performance degradation as well compared to both the original CUDA and also relative to the HIP backend. But I mean, the HIP versus Cocos HIP is pretty close to the original HIP, but you definitely see some of the impacts of the extra steps that you have to do with Cocos. We've also rewritten it in SYCL, where we have basically taken the original CUDA code and run it through the translation layer, and then which Intel provides, and then exercised it on a multiple different architectures. So right now we can run SYCL on the Intel GPUs, on the Intel CPUs, on NVIDIA GPUs, and on AMD GPUs, and we see comparable, well, almost comparable performance to the original CPU, the original CUDA version. Maybe it's 80%, or it's like 4 times faster than the original CPU versus 5 times faster for the CUDA version. But what's nice is that we see similar performances for the native backend as opposed to the SYCL backend for all these different platforms. And we can run it on all of these different backends without making any modifications really to the code. And there's one aspect of this that I'll get back to in a little bit, which has to do with random numbers. We have several different types of particles or events that we can run, and we see some differences. For example, when we run some top events as opposed to some electron events in the simulation, and there we don't see nearly as much performance speed up when running on GPUs, basically due to the topology of the events and the lack of inter-event parallelism, and the fact that you really have to load so much more data onto a GPU, which really slows things down. So one of the issues that we encountered when running SYCL with different backends is that when we first started doing this, there was really only one random number generator backend available, and that was for running on Intel hardware. And as we know, we use random numbers everywhere in high energy physics. So we spent some time developing interoperability layers to be able to run the random number generators on different hardware backends. So on both the NVIDIA backend and also on the AMD backend. And what's nice about this is that it is using the vendor provided libraries such as QRAND and RockRAND, and then the SYCL interoperability API to run the random number generator completely transparently. So from the user point of view, they don't need to change their code at all to be able to use these different backends. Of course, since it is using the vendor provided backends, there is some issue with reproducibilities of the sequences. So you may not necessarily get the same sequences using the NVIDIA backend as you would with the AMD backend, but we are planning on possibly tackling that in the future. Finally, one of the last thing that I'm going to talk about a little bit is event generators. Even though this is its own completely separate group inside of the HEP-CCE project, there is some linkage with the PPS in the sense that we have started trying to port MatGraph 5 to Cocos, so and as well as to CUDA. So there has been a CUDA port which has been under development at CERN, and we have taken this and started trying to make it work with Cocos with the CUDA backend as well, and as well with the SYCL backend. Sorry, not the SYCL backend, but with the SYCL version of MatGraph 5. And this has been very promising. We see, maybe not quite as good performance as the original CUDA, but the fact that we can run with different backends is actually, very, very heartening. And we're seeing some, very nice results that are coming out of this group. So let me try to just distill a little bit of the things that we have learned from these different explorations. We've spent most of our time at this point really looking at Cocos. So we really have, I think, the most experience with Cocos. And it really has a very high level programming model, which as architectures evolve, I think will give us the ability to get better and better performance, or reasonable performance really, on new architectures as they emerge, because it has a very high level interface to underlying structures like data structures and algorithms. It allows the Cocos developers to actually implement things with considerable performance on the different architectures as they emerge. There are backends for basically everything we can run on right now, except possibly FPGAs. FPGAs, I think, are a little bit under development with Cocos, but it's definitely not well supported. And we can run on NVIDIA, AMD, Intel GPUs, serial CPUs, OpenMP, and MP threads. And the APIs have tended to be very stable, especially of the earlier versions. It has a very, very responsive developer community with, you ask a question on Slack and you will get responses very quickly. And they've been very helpful when we've been developing code, and we've even had a number of hackathons with them where they have, done deep dives into our code to try to improve things. Depending on the complexity of the code, you can see speeds that really approach the native backend. However, as the code complexity increases and as the number of features of Cocos, or of really maybe some of the reduction, the kernel chaining, things like that increase, the performance tends to drop. But still, running at 50% or 80% on a platform that you wouldn't otherwise be able to use, I think is still a huge gain. There are definitely some challenges that still exist when running or integrating with HEP experiments. One of the things is that it requires separate compile libraries for each individual device architecture. For instance, you can't use the same binary to target an NVIDIA GPU and an AMD GPU. You can choose one parallel GPU backend, or device parallel backend, one host parallel backend, and one serial. So you can run serial CPU, OpenMP, and CUDA, but you can't. If you want to run on an NVIDIA GPU, you have to recompile. The CPU serial backend is thread safe, but it's not really thread efficient. Up until now, it definitely had issues integrating with code that used TBB. Right now, they finally have a version that is thread safe, but it has a mutex to control behavior, which really limits performance. But this is being worked on right now. The support for complex types of arrays, such as multidimensional arrays, while they are supported, they aren't well supported for the types of things that we want to use, things like jagged arrays or, you know, complex structures of arrays or arrays of structures of arrays. And there's no unified or portable interface to things like FFTs, though these things are currently being worked on. SYCL is another really promising product. One of the advantages that it has right now over Cocos, I think, is that in theory, a single source and a single compilation will be able to target the different types of backends. Unfortunately, in practice, that's not really quite the case, because you really need still at this point different compilers to target all the different sorts of backends. And there are a lot of different compilers out there. There is the Intel compiler, the DPC++, but there's also the LLVM version, which has a CUDA backend and an AMD backend, but in order to exercise it, you have to do things at compile time. There's also HEP-CCE and you know, a number of other products as well, which can target different backends. The fact that it uses a DAG-based dependency graph to basically associate data products with kernels kind of simplifies the development of the software, so that you don't really need to do the direct transfer to a device the way you have to do in CUDA or in for instance, in Cocos. But if you do want to get really good performance, you will probably have to do something a little bit more in order to direct things, to transfer your data to the hardware at at the best possible time. It integrates very well with existing build systems like CMake and then Makefiles. And it also links well with existing binaries, which are built with, say, GCC, so you don't need to recompile your full stack. It will, as I said, it runs well on all our different backends. We haven't exercised the FPGA backend yet, though, so we can't really have any experience there. And there's a lot of really rapid development which is still going on. We see new features that are being added constantly, with things like execution on sub-devices, some support for concurrencies. We see atomic operations, and we also see better interoperability and more efficient acceleration with third-party libraries. One of the recent additions to our investigations has been what's called a STUDPAR, or the STD execution parallel. NVIDIA has relatively recently provided a compiler, NVC++, which is part of their HPC SDK toolkit, which will allow you to run the STD-PAR code on a GPU. In the past, you could do that on CPUs if you had just the right version of GCC and just the right version of TBB. And it's really hard to actually make everything work. But now we actually have a solution where you can run on GPUs directly. And in fact, NVC++ can target serial CPU, multi-core CPU, and also GPUs. Of course, they're only targeting CUDA GPUs, or they're NVIDIA GPUs. But it's still, a step in the right direction. It's still very, an early product. We can't compile root with it yet. There's definitely compiler bugs. It's not terribly well integrated with CMake. You have to write a bunch of, wrapper scripts to make it work right. And some things seemingly work fine in little standalone reproducers. But when I try to integrate that into more complex environments like fast Gallow Sim, where you have multiple shared libraries, things suddenly stop working, and we don't really understand why. Also, for instance, the multi-core backend, even though it works on the reproducers, it doesn't work at all in the fast Gallow Sim environment. So there's definitely some room for improvement there. But it does offer some kind of interesting upgrade and side grade paths. For instance, if you have CPU code, it's relatively easy to change it to executing on a GPU or on multi-core without having to do very much at all. And if you have your CUDA code, it's very easy to change that to execute on CPU or on multi-core environments. It doesn't really require very much at all to change the CUDA code to run with NVC++, because it is completely interoperable with CUDA code. So what you can do is actually you can easily migrate little bits of it at a time and still call direct CUDA functions from within NVC++ kernels. And it also uses a USM for the memory management. So what you have to do if you really actually want it to run with all the different backends is, instead of allocating all your code to run to get transferred to a GPU with CUDA malloc or something like that, you have to allocate it all in a structure on the CPU, which then gets migrated automatically for you by NVC++. And there are also some small issues there that, if you're compiling both with GCC and NVCC and NVC++, because you have different parts of your code which are written in different languages or with different compilers, you have to be very, very careful that anything which gets offloaded by NVC++ has to be compiled by NVC++. Otherwise, the code doesn't get instrumented and it doesn't get offloaded properly. It's not quite as performant as the original CUDA. We're definitely, if you look at some of these plots, we're definitely seeing the performance is a little bit degraded. And some of it might be because of the USM, and some of it might be because of how it's using thrust as the back end. It might be because it's still an immature compiler. We're still looking into this. Also, there is definitely an impact in build time. It's maybe twice as slow as NVCC, so as compiling something directly for CUDA. One of the interesting things, though, is that when you take with fast Gallow Sim, we had original CPU code, we translated into the CUDA. We took the CUDA code, translated that into NVC++. And if we compare running the NVC++ code on a serial backend, it was faster than the original CPU code. So that's kind of nice. This is kind of where we are right now with our different test beds. These shades of green and red aren't all the same, frankly. There's still development work which is being done in Patatrack for Cocos and in Wirecell. Sickle has started to come into the game. We are seeing new development with OpenMP. We've just started with Wirecell and fast Gallow Sim looking at OpenMP. I haven't included ACTS here yet because it's a very recent addition to HEP-CCE. But hopefully, the next time we give one of these talks, we'll have a whole row for ACTS as well. And STD-PAR is also starting to make inroads, and we hope to see some more green boxes as well as for Alpaca. So, looking forward, where are we right now? We're about 2/3 of the way into our three-year journey. We've done a lot of work with PPS and iOS. And the event generators and the complex workflow groups are really taking off as well. We have made some pretty significant developments and made some nice investigations and actually started learning a lot from these different performance and portability studies with the different test beds. We've presented our work in a lot of different venues like this one, and also larger conferences and ACAT and CHEP and supercomputing. We've had some very good feedback from both the high energy physics community and also some very interesting interactions with the software and the hardware providers. So with with NVIDIA and AMD and Intel, both from their software groups and their hardware groups. We continue to ramp up our effort, which is still a big challenge these days, and we continue to recruit more developers and experts from both the experiments and from DOE and from Oscar. We have new hires at both postdocs and summer students. And in the in the long term and the short term as well, there's definitely potential for very significant impact on the experiments. What's important to remember, though, is that we're going to produce strategies which are tested on prototypes in order to really bring this thing back into the high energy physics environment. It's going to take direct integration with the experiments again, with a lot of back and forth to take the lessons that we have learned and then integrate it back into the large projects to see the benefits from all this work. And that's it. Thank you, everybody. And I'll take questions.
Great. Thanks so much, Charles. That was really interesting. There's a ton of stuff going into the live notes. A lot of updates for the table on slide 9. I think you're going to have to use more colors in the future, but I think we shouldn't really dwell on those things because they're not things that are directly in our control. Maybe Andrea, you had written down some notes on Patatrack. Maybe you wanted to ask that question now.
No, I just wanted to point out that Alpaca itself has some updates with respect to what is in the slides, and also Patatrack has some improvements with respect to what is in the slides. So basically, the Alpaca port is complete. We are now working on the last 5% of performance.
Excellent.
Thanks a lot. Okay. Attila, let's move on to you.
Yeah, actually, Alpaca and Patatrack would have been one of my questions. But with that out of the way, I guess I just have to comment that I think even in the medium term, we will have to make our peace with portable code only being portable at the source code level. Because even if things happen in the most magical way, I think the best that we can hope for is sort of what we can do with well-written C++ code on ARM and x86 at the moment, where we would have a single code base and we could just compile it for both CPU architectures. Maybe in the very end, we will have like fat binaries as we used to do with x86 and something else. But yeah, I think this we might have to just be happy with if we can arrive at this point.
Yeah, no, I completely agree. I really don't see any way that any of these products is going to be able to have a single binary that will run on all the different backends. And that's going to massively complicate our, our software distribution and our job submitting systems, where you have to make sure that you have the right binaries at the right places.
It is painful. I agree, but yeah, especially since, as you know, the Intel compiler at one point was able to do this. It lost this ability since quite a while. But yeah, just like with ARM and x86, I think we have to deal with it.
Thanks, Attila. So maybe we take the next question from the live notes. So John, you were asking about the, I think the ATOFAST work in particular.
I axed that question because it was just a comment. My general comment was performance is not the be all and end all. If it's impossible to write the software or maintain it, it's useless, but it does matter. So how much do we understand, or how much do we have a reasonable understanding of the origin of the gap between the performance between the portable application and the hand-tuned CUDA applications? There is a partial answer.
I'm sorry, I missed that last section. You said there is a...
M. Lin has provided a partial answer.
Yes. I don't know if you wanted to expand on that.
I can't see the chat right now.
Right. So this is just a case study with the partial porting of Wirecell, and we did have the CUDA version for that part of the porting. And what we've discovered is that some of the Cocos kernels are like 3 times slower than the CUDA kernels. And usually the kernel launch time in the Cocos implementation is longer than the CUDA version. And in some cases, Cocos seems to have some additional synchronization that also contributes to the longer runtime. But for the full porting, we don't have the Cocos, we don't have a CUDA version for comparison. So that's why it's not shown here, the native CUDA implementation. Does that answer your question?
I think sounds to be like the best answer we have at the moment.
I mean, there's definitely extra stuff that you need to do when you throw in one of these portability layers, especially we've noticed it with Cocos. Things like, initialization of their data structures and how the offloading is actually performed. And that's why I was, we could have spent a lot of time going through all the performance differences that we've seen in the different cases. Patatrack was really suffered much more so than fast Gallow Sim because of the different types of features and the different types of data structures that were being used. So depending on how the code is written and how tuned it is, because you can take the Cocos code and you can actually make it look more like CUDA, for instance. There are different things that you can do to make it look, or to exercise the CUDA aspects of it, but then you lose the portability. So you can in some ways make Cocos with the CUDA backend perform almost as well as CUDA, but then you're not going to be able to run anywhere else. So when you start throwing in some of these extra layers in between, which provide the portability to the different backends, that's where you start to lose performance.
Thanks for that extra clarification, Charles. So I think we should move on now. Ben asked an interesting question, but he had to run to another meeting, so maybe you could look at the live notes after the fact. Vince, you had some thoughts on strategies and metrics. You want to bring that up?
No, I noticed on slide 24 that Charles did mention it. It was just, some of the metrics involved integration into experiments and requiring to recompile the whole software stack and so on. So I was just wondering if there was a plan to do some sort of experimental integration to get a better handle on this.
You mean from, say, Atlas's or CMS point of view?
Yeah, exactly. I mean, how easy is it to integrate one of these portability APIs into something that consists of millions of lines of code, for example?
So, these things have already started being tackled by the different experiments on their own. And I don't think it's necessarily within the purview of the HEP-CCE group to solve all those problems, or rather to do the actual integration ourselves. I think by taking these test beds, we expose a fraction or a subset of the integration problems. For instance, when we took Patatrack and fast Gallow Sim and tried to integrate Cocos and Sickle into the build environments that came with those different packages, we saw some of the issues, and we can certainly take the lessons learned there and feed them back to the experiments. A number of these things have already been done. For instance, you can run, there's already the infrastructure to run Sickle code inside of Atlas reconstruction inside of Athena. I'm not sure, though I'm sure the level to which this has been done inside of CMS, though I'm sure that it has been done. Maybe somebody like Chris can comment on that, but I would not be at all surprised if that has been handled.
Yeah, I'm just wondering, like, for example, impact on other existing code, threading execution model, event data model. Do these test beds really encompass all of these criteria that you're aiming to evaluate here in terms of metrics?
Well, we're obviously not going to be able to do everything. We're not going to be able to test all the data models that exist on the different experiments because they're not necessarily represented in these test beds. But we can certainly say things of, right, it works great with one-dimensional flat arrays of ints. But when we start, making jagged arrays of complex numbers, we run into these issues. So we, like I said, we're going to produce general strategies, which we can then feed back to the experiments. And it will be up to them in the end to exercise all of the different requirements for all the different types of issues that they encounter.
Thanks, Charles.
Great, thanks. So time has rather run away from us, but we could maybe take one last quick question. There's a few, I see that quite a few things are appearing in the live notes, which is great if that discussion is there. Anyone else want to raise a question in the meeting or make a comment? Okay, I think not. So great. Then thanks to all of the contributors today, both speakers and people who have written down questions and people who have asked questions. So I think we should close the meeting here. We will post the video up to YouTube and put it onto CDS as well, so that if you want to review the meeting, you're certainly able to do so, or if you know people who are in different time zones. And let me close just by saying that reminding you that the next meeting that we will have will be on the 9th of March. And funnily enough, we will be continuing the discussion about PathoTrack and ACTS. So we have a nice broad theme going through the first couple of meetings of the Compute Accelerator Forum this year. So with that, thanks again, and see you next time. Bye-bye.
Bye.
Bye.
Thank you. Bye-bye.
Bye.